Let's take a look at aqueous solutions, part 3. In this section, we're going to focus on acids and bases. For right now, let's just consider what are known as Arrhenius acids and bases. These acids produce H plus ions when dissolved in water, and bases produce OH ions when dissolved in water. These acids and bases are broken into two groups: strong acids, which completely dissociate in water. This means that the compound completely breaks up into H plus ions and whatever the negative ion is, or for the base, the positive cation and the hydroxide ion. The examples you see here are hydroiodic acid and potassium hydroxide. Weak acids and bases only partially dissolve in water, which means that they do produce either H plus or OH minus ions, but they also maintain some of the original acid and base. What we are most concerned with is an acid-base titration. A titration is a volumetric technique for determining the amount of a certain substance. A known volume of a given solution that has a known concentration, we call this the titrant, is added to a substance to be analyzed in order to determine its concentration. We call this the analyte. These are two very, very important terms. We want to make sure we know these definitions. When the moles of the analyte are equal to the moles of the titrant, we say that the solution has reached the equivalence point. The equivalence point simply means that we have equal number of moles. In order to determine when we have reached the equivalence point, we use an indicator. These are common indicators like phenolphthalein, which change color once the reaction has reached the equivalence point. Let's look at an example. A student wishes to determine the concentration of a 100 milliliter sample of vinegar, which is an aqueous solution containing acetic acid. This is our analyte, what we are analyzing. The student titrates the solution with 16.58 milliliters of 0.5062 molar sodium hydroxide. This is our titrant. It's what we know. What is the concentration of acetic acid in the solution? First thing we want to know is what is the actual net ionic equation for what's going on in the solution. So our acetic acid is combining with our sodium hydroxide to form water. These are the only ions that are relevant. The sodium is a spectator ion, as is the acetate ion in acetic acid. The first thing we can do is take the volume of our titrant and multiply it by the concentration of the titrant. That gives me moles of sodium hydroxide that were used in this titration. Given that we have a 1-to-1 ratio between the acid and the base, that means there are also 0.008 moles of hydrogen ions. Given that this is equal to the moles of acid, we can divide by the sample of vinegar, which is our 100 milliliters or 0.1 liters. Dividing moles by liters gives us molarity, which in this case becomes 0.08 molar. Let's take a look at an AP example. The oxalate ion, or C2O4-2, is present in the guava fruit, and its concentration depends upon how ripe the fruit is. The concentration of the ion can be determined through an acidic redox titration with a permanganate solution. The unbalanced reaction is shown below. A student is given 25 grams of guava fruit, and they isolate 20 milliliters of guava extract. The student uses a 10 milliliter pipette to transfer the extract to an Erlenmeyer flask, where we add sulfuric acid and water. The student fills the burette with 0.25 molar KMnO4 solution, titrates to a slight pink equivalence point, and records the following data. First thing we need is a balanced chemical reaction. So taking a look above, our manganese ions are balanced. Our carbons are not. We have 2 carbons on the left and only 1 on the right, so we're going to throw a 2 in here. Looking at my oxygens, I have 4 plus 4 gives me 8 oxygens on the left. On the right, I have 4 oxygens from my carbon dioxide now, plus 1 from my water is only 5. So I'm going to throw a 4 in front of water to balance my oxygens. That now gives me 8 hydrogens, which I can easily balance over here. B and C we are going to skip for right now as they refer to redox reactions, which we will cover in the next section. Throughout the titration, the student observes significant fizzing, but the fizzing decreases and ultimately subsides at the equivalence point. Explain this observation. For this, think about a soda. It fizzes because it contains carbon dioxide. So as this reaction occurs and the titration takes place, carbon dioxide is produced. At the equivalence point, no more carbon dioxide is produced, and we see a reduction and then ultimately a stopping of fizzing. In E, we want to calculate the concentration of the oxalate ion in our 10 milliliter sample. In order to do that, we need to figure out what's going on. So the first thing we can do is we can take the final volume of our titrant and we can subtract the initial volume from the burette. Together, this gives us 10.32 milliliters, or 0.01032 liters. We knew that the concentration here was 0.25 molar, so multiplying the two together, I can determine how many moles I have of my titrant. I have 0.0026 moles of the MnO4 minus solution. I know, based off of my balanced equation, that is in a 1-to-1 ratio. That is in a 1-to-1 ratio with my oxalate ion. So that tells me then that if I have 0.0026 moles of manganate, I also have 0.0026 moles of my oxalate, or my C2O4. Given that I know that, I can now divide my moles by my volume, again making sure to convert to liters, so I end up with 0.258 molar. We want to know what the mass percentage of the oxalate ion is in the guava fruit sample. So now that I know what the number of moles of oxalate ion are, I want to take the moles and convert them to grams. So I'm going to take my 0.0026 moles, and I'm going to multiply that by the molar mass of the oxalate ion. So multiplying by 88 grams. I find that I have 0.2288 grams of oxalate ion. Dividing that by the mass of the guava sample, which we were told was 25, we're going to multiply by 100 in order to get a percentage. Doing this math, we find that we have a very low 0.92%. In G here, we're asked the amount of water added to the flask is not significant, to please explain. In this case, it does not really matter how much water you add, since the only thing that matters is the amount of ions that are in solution. Adding more and more water will not affect the amount of oxalate ions in solution because it's not reacting. We're going to go ahead and skip over H for this one as well, given that we've talked about the preparation of solutions before.